Okay, let's just dive right into this explainer and, uncover the absolutely fascinating physics behind collisions and safety. I mean, if you've ever wondered how on earth engineers design cars to actually survive high-speed crashes or why sports equipment looks the way it does, well, you are in the exact right place.
So here's our game plan for today. We're going to explore the physics of impacts, define what momentum actually is, and break down the impulse momentum theorem. After that, we'll apply all of this to real-world safety engineering and then wrap the whole thing up with a quick concept check.
All right, Section 1, the physics of impacts. Let's start with a little scenario to really anchor our learning here. Think about a car suddenly slamming on the brakes, or maybe a basketball player catching a super fast pass. What exactly determines how hard that impact actually feels? Like, why do airbags and helmets actually work to reduce injuries? Well, don't answer just yet, but keep this in the back of your mind as we start building out our physics toolkit.
Okay, Section 2, what is momentum? To solve our little mystery, we first really need to understand the fundamental quantity of motion.
Now, momentum is a concept you probably hear all the time, right? Even in sports broadcasts when an announcer is like, "Oh, this team really has the momentum, and they're going to be impossible to stop." Well, in physics, momentum quantifies exactly that. It's literally just mass in motion. The formula is P equals m times v. So P is momentum, m is mass, and v is velocity. Basically, any object with momentum is going to be hard to stop, and if you have a greater mass or a greater velocity, you're going to have a massively greater momentum.
Now, a quick aside here. We got to be super careful not to confuse mass with weight. It happens all the time. Mass is simply the amount of matter in an object. It's a constant scalar quantity measured in kilograms. Doesn't change no matter where you are. Weight, on the other hand, is a force that changes depending on gravity. So for momentum, we're taking that constant mass and multiplying it by velocity.
Section 3, the impulse momentum theorem. This is where we figure out how to actually change an object's momentum.
To bring a moving object to a total halt, you absolutely have to apply a force against its motion for a specific period of time. And that introduces us to a new concept, impulse. Honestly, impulse is simply the force applied to an object multiplied by the time interval over which it acts.
And this brings us to a really brilliant connection. The impulse experienced by an object actually causes and is literally exactly equal to the change in its momentum. Imagine a football halfback sprinting down the field and taking a huge hit from a defensive back. If that halfback experiences, say, a leftward force of 800 newtons for 0.9 seconds, well, the impulse is 720 newton-seconds, and that exact impulse perfectly equals his total change in momentum. It's like a perfectly balanced equation in real life.
So looking at our equation where force times time equals mass times change in velocity, we uncover this crucial inverse relationship. For a fixed change in momentum, increasing the contact time directly, and I mean directly, decreases the average impact force. Picture landing on a super thick gymnastics mat versus a hard concrete floor. Your change in momentum is exactly the same in both scenarios, right? You go from falling to totally stopped. But that mat significantly increases the time it takes for you to stop. Mathematically, that means the average force applied to your body drops dramatically.
Section 4, Real-World Safety Engineering. Let's see how this physics foundation literally saves lives.
You know, safety engineers are essentially acting as time extenders. Using Newton's first law, they know a passenger in a crash is just going to keep moving at the car's original speed until a force acts on them. Then, using the second law, they know that extending the time of that collision reduces the force. So they use these exact principles to design seatbelts, airbags, sports helmets, the whole shebang. These devices aren't just there to cushion you. They deliberately buy your body more time to slow down. More time means less force, which ultimately means fewer injuries. We see this applied just brilliantly in modern vehicles. In a car crash, intentionally designed crumple zones fold in on themselves, kind of like an accordion. So instead of the car stopping instantly against a rigid wall, this controlled crumpling buys precious fractions of a second for the cabin to slow down. Just by increasing that stopping time, the people inside experience way less force. It is no exaggeration to say this can literally be the difference between a survivable crash and a fatal one.
All right, Section 5, Concept, Check, and Review. Let's see how much of this we've locked in.
So take a moment to predict the answer to this one. Thinking back to our crumple zones and gymnastics mats, what happens to the average force when the contact time increases? Got an answer? Well, the average force drops significantly. Why?
because time and force are inversely related whenever the total change in momentum stays the same. Let's actually trace through a quick practical math example to really cement this. Imagine a 50-kilogram passenger. Let's call her Jennifer. She slams on the brakes to avoid hitting a deer. She hits the airbag at 35 meters per second, and the airbag brings her to a complete stop in exactly half a second. By manipulating our impulse equation, we plug in her 50-kilogram mass, her 35 meter per second change in velocity, and that 0.5-second stopping time. If we calculate that out, the exact average force exerted on her is 3,500 newtons. If we didn't have that extra time provided by the airbag, wow, that force number would be absolutely catastrophic.
I'm going to leave you with this final kind of provocative thought. Consider why a car that bounces off a wall experiences a far greater impulse and much larger forces than a car that just simply crumples to a stop. Think about that change in velocity. When you just crumple, your speed goes to zero. But in a rebound, you go to zero and then you suddenly accelerate in the complete opposite direction. That requires a massive change in momentum, which forces a massively higher impulse and just way greater force on the car and the passengers. So the next time you strap into a car or put on a helmet, you're going to know exactly the invisible physics keeping you safe.